There's a number of vulnerabilities that target the Internet Protocol. Now remember, the Internet Protocol operates there at layer 3, the Internet layer, or the network layer if we're talking OSI. And these vulnerabilities vary. We're going to take a look at each one of these. We have the man-in-the-middle attack. We have session hijacking. We have IP address spoofing. We have DOS attacks, or denial of service. We have distributed denial of service attacks, the Smurf attack, and resource exhaustion. Let's go ahead and take a look at that first one, a man-in-the-middle attack, and see how it targets IP. A man-in-the-middle attack is the type of an attack where somebody who is malicious inserts themselves into the middle of a conversation between two systems. So imagine you have A and you have B, and they're talking to each other, and then all of a sudden C ends up right in the middle of this conversation, and all of your traffic starts to move rather than directly between A and B. Your traffic starts moving through C. C has inserted themselves into the middle of that conversation. A doesn't know it and B doesn't know it. Now, how bad can this be? Well, it can be really bad. See, this is an eavesdropping type of attack that exploits the real-time traffic, right? So A and B are having this conversation, traffic's flowing back and forth. C gets in the middle of that conversation and starts to capture that traffic. The end-to-end connectivity is broken. A and B don't know it. And C is able to start capturing all of the traffic. Now, what kind of things could happen here? Well, okay, let's say that A and B are trying to set up maybe some encryption, and they're going to exchange their keys. So A says, all right, send me your key, and then B sends the key. Boom. Okay, so now what happens? C, right there in the middle, now has a copy of that key. So using that key, we encrypt some traffic. So all of a sudden, you've got encrypted traffic that's coming across. And normally, the two parties, A and B, would be the only ones that can read that encrypted traffic. Well, C grabs that traffic and changes it, can decrypt it, read that traffic. Let's say that it's a transaction involving money. Let's say that the transaction is sending money to a specific account. Well, that attacker that has placed themselves in the middle of this session can now change the destination account number where those funds are going. So there's a lot of people that are susceptible to attacks like this. It could be financial institutions. That's one example. The example here of changing the direction of money, sending money to a different account. But it could also be, anybody that wants to sit in the middle and capture traffic, perhaps to replay it and see what you're doing. Or if they want to replay conversations, maybe you're doing messaging, maybe you're transferring files, they want to capture those files. Maybe it's intellectual property that is very important to the organization. Now, this is a form of eavesdropping, as I mentioned, and it's just one example of a man-in-the-middle attack. There are other forms of session hijacking, man-in-the-middle type attacks. We actually are going to talk specifically about session hijacking, but understand that session hijacking is yet another form of a man-in-the-middle attack, but it could be an attack known as sidejacking. This attack would be sniffing packets to steal your session cookies and then using those cookies to get unencrypted login information, even in the situation where a website might be secure. There's also a session hijacking method called Evil Twin, and this deals with a Wi-Fi network that appears to be a legitimate network. In fact, people put a Wi-Fi pineapple in their backpack and they walk around advertising AT&T wireless. And what happens? Well, some of your phones are set up to automatically connect to these networks. And then all of a sudden they're able to intercept data. And of course, sniffing attacks where somebody is intercepting your traffic using an application or some type of software to view what's going on. Again, these are just some examples of session hijacking as well as man-in-the-middle attacks, both vulnerabilities that are targeting the IP protocol. Now, how does this happen? Let's just look at it for a moment from the IP level. What's inside of an IP header? Remember, the IP header has a source IP, a destination IP, and a protocol. Those are going to be the important parts, right? Protocol tells me if it's TCP or UDP, and the source and destination IP have to do with the routing of my traffic. Okay, so we're dealing specifically with the Internet Protocol. How can something change my path between A and B? How can that session get hijacked? How can a man-in-the-middle attack ensue? Well, very simply, we can have that attacker, which we said was C. The attacker can change either the source or the destination IP. So if there's a way that they can capture packets, they can make themselves appear to be someone else, or just simply place themselves passively in the path, well, then they're able to capture that traffic. But again, we're talking specific about Internet Protocol vulnerabilities. So if we're going to hijack a session, we're going to be modifying either the source or the destination IP, or perhaps both. Now this could go up a layer, right? It could go into the DNS resolution. If DNS is resolving the wrong website, then you have somebody who could be sitting right in the middle there. That's one example. Let's take a look at another example of a vulnerability that attacks the Internet Protocol. How about IP address spoofing? All right, so how do we do this? In fact, there's more involved in IP address spoofing than just layer 3, just the internet layer of that TCP/IP stack. And that's regardless of whether it's a man-in-the-middle attack or a session hijacking attack. Again, let's just talk about IP address spoofing. So we have A, and A has an IP address of 10.0.1.10. And their default gateway is 10.0.1.1. Okay, so the gateway is a router, remember? Gateways are routers, they're layer 3 devices. This is all kind of knowledge that you should have already, right? Understanding basic networking, basic Cisco IOS, that kind of thing. So A is our PC. A is on a switched network, so there's a layer 2 device in here, and then there's a Cisco router on the network, and that router is the gateway. Now, how does normal routing work whenever A wants to send something to someone off the network? Well, there's a couple of things that happen first of all. So the first thing that A does is it looks to see if it's on network or off network. And if it's off network, then the second thing it does is it looks for ARP resolution for the default gateway, and then it's going to forward the packets to that default gateway. Let's back up a step. The first step, whether or not we're on network, how's that happen? Well, we have to resolve a name, first of all. So let's say A wants to get to Cisco.com. We're going to use, do you remember the protocol? DNS to resolve an IP address for Cisco.com. So let's say that the IP address comes back, and that address happens to be something like 192, I'm just going to use a private IP address space here, 192.168.1.100. Okay, so now A will do a logical AND between its own address, the 10.0.1.10, and the 192.168.1.100 address, and that determines that, hey, these bits don't match up, we're not on the same network, so I have to send it to my gateway. The gateway has been configured already, generally two ways that that's going to happen. That could have been done through static assignment, or that could have been done through DHCP, which is probably more common. So you've gotten a DHCP address, you've gotten a gateway, you've gotten your DNS, all that stuff comes from the DHCP server. And so now you decide to forward this to your default gateway. But before you can form that Ethernet frame as you pass it down the protocol stack, remember that encapsulation process? Before you can put your layer 2 header information on, or your link layer header, you need to do an ARP, and you need to find the MAC address of the default gateway. Okay, so you ARP, you get the gateway's address. So let's just assume that in this case, the default gateway's address is 0001.000.1.0.0.0.1. We're just making an address up here for simplicity's sake. Okay, so now you've got ARP resolution, and that ARP resolution says 10.0.1.1, my default gateway, is that MAC address that we just talked about. Okay, so now you can forward this over to your gateway. Your gateway is going to get it, and the gateway is going to forward that packet on to another destination, right? To the next hop router based on its routing table, and it's going to move that traffic through the internet. Okay, so that's what we want. We're trying to get to 192.168.1.100, which for our example's purpose is Cisco.com. All right, now we have an attacker come onto the scene. And so the attacker is plugged into our switch network. And the attacker, this black hat guy here, he has a MAC address of 0002.0002.0002. What he's going to do is he's going to start to spoof an address. So he sends out a gratuitous ARP. This is an ARP before anybody asks for an ARP that says, "Hi everybody, I just want to let you know that I, 0002.0002.0002, I am 10.0.1.1. He's lying to everybody and saying he's the default gateway. He's just started spoofing the gateway's address, right? He's saying, I'm the gateway, send traffic to me. So boom, traffic goes to him as the default gateway. Well, he knows where the real gateway is and he forwards it. And now all of a sudden, not only do we have an IP address spoofing attack, but at the same time, we have a session hijacking attack because he's right in the middle. Oh, and don't forget, yes, that's a man-in-the-middle attack as well. He is sitting right in the middle, capturing all of that traffic. This concept of IP address spoofing, pretending to be someone that you're not, this leads us to another type of attack that makes use of IP address spoofing, and that is denial of service attacks. So one common denial of service attack utilizes all of the resources in sending a SYN message and spoofing the source address. Now, again, this is a very simple activity. Here is a server. This server, we're going to stick with the fact that this is Cisco.com. And that Cisco.com server is on the internet somewhere, and you've got this attacker who's sitting out here. This is the bad guy. He is sending a TCP SYN message to that Cisco.com server. Now, his real address, we're just going to make something up. It's 198.13.10.1. I'm just picking some random address here. That's his real address. And so when he makes a connection to Cisco.com, if we look at those headers, we got to remember how those headers are built, right? So we have our application data, whatever it is. In this case, we're not sending any app data. Recall in our end-to-end or our host-to-host flow section, we talked about how the application says, hey, TCP, I need a complete connection set up so that I can send some data. And then TCP says, okay, I got to do a three-way handshake. Let's go ahead and do this. Hey, IP, please send this message over to, and then it's got the IP address of Cisco.com, and then the IP layer says, okay, I'll go ahead and form a packet. Hey, layer 2, can you send it? Layer 2 is going to do the ARP, find the gateway, and then forward it towards the gateway in this case. Okay, so what happens here? Well, again, this guy is an attacker, and he's going to spoof an address. So he has some very specific software. For example, EtherCap. We use that specific software and we say, you know what my address is, and I'm going to pick a fake address. Now, what kind of address could I use? Well, I could use one of the internet bogons. What is a bogon prefix? Well, a bogon prefix is a route that shouldn't appear out on the internet's routing table. So bogons are kind of defined as these Martian addresses. They're addresses that would be defined in RFC 1918, RFC 5735, RFC 6598. They're blocks of addresses that are not allocated to a registry and that should not be seen. So for example, let's say that we choose the bogon address of 192.88.99.5. Okay, this block of address space is actually allocated to the 6-to-4 relay anycast address that's found in RFC 3068. So that's not what we're using it for, but we're going to say that this is the source address for a TCP SYN. So as we pass that traffic down, the protocol stack. This bad attacker that's using an application like EtherCap is going to craft the packet so that the source IP is this bogon, or this unused, unallocated, not supposed to be seen address. Now, the destination IP in that packet is going to be the IP address for Cisco.com, and we're going to send that packet on its way. Okay, so now this is a DOS attack, right? Denial of service. So how are we denying service? Okay, well, the Cisco.com server receives that request, so boom, it comes across, he sees it. He says, okay, I got to formulate a SYN-ACK, and he sends a SYN-ACK. Well, that took some resources, and now I'm waiting for an ACK to finish that three-way handshake. But now this attacker who's bad, he does this several times. He keeps sending these TCP SYNs, and maybe he's using that same source IP address. Maybe he's using the next address, .6 and .7 and .8 and .9. But they're all coming from the same guy. Okay, so if that's the case, this is a denial of service attack, and eventually the server is going to run out of resources. His CPU is going to be maxed out because he's trying to handle these requests, and also he's not going to have enough resources to actually open up another port slot to handle the request. So again, this is a bad situation. That's just one example of a denial of service attack where spoofing is involved. Now let's take that a step further with another IP vulnerability that's on a larger scale. Now this would be a distributed denial of service attack. This has all the characteristics of that DOS attack, only rather than having that single attacker going against that Cisco server or that whatever server it is, we have many attackers, and they're all over the globe. And in a coordinated effort, they launch an attack at the same time against that server. See, this gets us into botnet type activity, where somebody is using a command and control channel to talk to each one of these machines and initiate that attack at the same time. But the fact that it is distributed across the internet makes it very difficult for that server or the network that that server's on to block the denial of service attack, because it's not coming through one provider, it's not coming down one path, it's coming from multiple locations. Again, just another example of an attack that we see at layer 3. Now, another example of an IP layer attack is the Smurf attack, and this is really a distributed denial of service attack. It just has a very specific name, Smurf attack. And this attack uses a large number of ICMP packets with the victim's spoofed source IP address. And what it does is we broadcast that onto the network. We send it to a broadcast address, trying to get a bunch of replies back to this spoofed address. Can you see how this attack is using multiple vectors? It's using address spoofing. It's using distributed denial of service, you see? So let's take a look at how that would kind of play out. So we have a device on the network that's just minding his own business, and his address is 10.1.1.1. And then we have multiple devices on the network that are going to send out this Smurf attack. And so what they're doing is they're going to send a directed broadcast. They're going to send a message with the destination IP address of 10.1.1.255. That's a directed broadcast address for the 10.1.1 network. Now, the source is going to be spoofed by each of these machines, and it's going to be 10.1.1.1. So any other machine that sees this, all the machines in the network that see this, they're all going to reply back to that one device and utilize all of his resources. Again, an attack that's designed to cripple a machine using the headers of IP, Internet Protocol. All of these, at some point, can result in resource exhaustion. There are specific resource exhaustion attacks. But this gives you an idea of how we have a number of attacks that are going to target the Internet Protocol layer.